Hello, and welcome to the course. This clipboard is what I like to use in place of a chalkboard when I'm recording from home, and I like to start each video with a, like a title thing, so you know you're looking at the video you want to be looking at. And there goes the focus. Come back. Okay, that was slightly annoying. In a lot of these videos, I come out as a disembodied voice as the camera's pointed at what I'm writing. So just in case anybody was curious what I look like, we'll do this part of it this way. The way I always start out a course is to spend a few minutes going over the syllabus. I try to minimize that, and it always ends up being more than a few minutes, but I'll see if I can control myself this time. I'm just going to hit a few high points. You should read the syllabus yourself, not only in my course, but in any course, because the syllabus is the rules of the game. And, you want to know what the rules are if you're going to play the game. So by the way, there's usually 4 handouts that I give out right at the beginning of each class. People walk in the room and I say, take one from each pile as you go by. There's the syllabus. There's the formula sheet, which will be your constant friend and companion as you, well, for one thing, you're allowed to use this on any kind of a test. But aside from that, it's a useful reference when you're doing the homework or working on a lab or anything like that. That one you definitely ought to print out a hard copy of. It's only 8 pages long. If you have any trouble printing things, let me know. But there's the syllabus, the formula sheet, the lab book, which I use the word book rather loosely. It's actually just about 45 pages with a staple in the corner, but it's the instructions for all of the lab experiments. And finally, a packet of lecture notes, which we'll get to in a few minutes. But you can find all of that and more at the website in the email that I sent you. When was that? Around August 7th or 8th or something like that. Or if you just go into Physics 131 in Blackboard, under announcements, that's where the email came from. It's under announcements in the course. You can also get the address of the website from the syllabus, which is under syllabus in Blackboard, because we're doing a lot of things paperless this time around. So when you go to the website, you'll find all of the handouts there. You find solutions to all the homework problems there, and that's the go-to place for all that sort of thing. So anyhow, the syllabus, maybe you've got a copy in front of you and you can kind of go along with me. I've got another little laptop over here where I'm looking at it right now myself. Starts out with contact information. The best way to contact me would be email, as in the Genesee EDU email. I rarely look at the messages in Blackboard. Really, the only thing I use Blackboard for is to post these videos. So if you want to like Zoom with me so we can interact and you can show me your work and that sort of thing, that's probably a good idea, but maybe send me an email first so we can work out what time we're going to do that and get it all set up and that sort of thing. Very few people did this. I'm not sure anybody did this the reason nobody did this last spring was I was working from home, but I intend to have my office hours in my office, assuming that the epidemic doesn't get worse and they don't throw us back out of the building again. I've been in my office exactly twice since spring break at this point. Anyhow, I was trying to keep this short. So email me, ma.crittenden@Genesee.edu. And when we're doing things remotely like this, I tend to check my email more often than when we're doing things regular. So you might even get a response evenings and weekends if you're lucky. Maybe not if you're not so lucky. We'll see what I'm doing that day. Um, it lists 5 required items. First of all, the textbook. People often ask, do I need to buy the textbook? And I always kind of stumble over the answer because I'm not quite sure what to say. Um, all of the written homework is in handouts. Years ago, I got tired of dealing with publishers who come out with new editions of the textbook every 3 years, just strictly to keep people from buying used books because they don't make any money on used books. Now, in some subjects, yeah, books get obsolete. In physics, what we call modern physics, the stuff that we cover in Physics 133, quantum mechanics, that sort of thing, that's 100 years old at this point. It's getting to the point where the word modern doesn't seem to mean the same thing to physicists that it does to everybody else. So anyhow, the point is, a copy of the textbook that's 20 or 30 years old is fine. Everything in there is still there. It's just been shuffled around and rearranged so they could call it a new edition. What I suggest, it doesn't seem like people take me up on it very often, but what I suggest is just get an old edition. What's the current edition now? 10th edition. So let's say you go on eBay and somebody's selling the 7th edition for $15. That might be a good way to go. Okay, as I said, all the written assignments are on handouts because I got tired of redoing my assignments every 3 years when they scrambled things around. And what the textbook for is to use for a reference, okay? Lecture notes are kind of skeletal. The textbook fills it out. Also, sometimes it's good just to hear things phrased differently. You sit here and you listen to me explain something, and when it's done, you're scratching your head going, I have no idea what that idiot was talking about. So you read the textbook and maybe it explains it better there. If you need the book to study, you should have the textbook. Other people get to the end of the course and say to me, are we ever going to use that book for anything? Because I haven't opened it yet. So what you might want to do is go a few weeks into the course. Nobody says you have to buy it right at the beginning. You might want to go a few weeks into the course and see how it's going. Or if you want the page numbers on, the reading assignments and the syllabus to match up with the book, you might want to get the new edition. If you're if you have several other courses where it's the same publisher for the textbook, you can get the current edition of the textbook electronically for nothing. There's this thing, I think they call it, Cengage Unlimited, where it's, I don't know the exact price. It's like $100 or $150, something like that a semester. And it gives you access to their entire collection, like thousands of books or something like that. So if you've already got that for other courses, you can get the textbook for no additional charge because it's in there. So you got all kinds of different options. It's complicated and confusing, but anyhow, that's what there is to say about the textbook, I suppose. Calculator. Many of you already own an elaborate programmable graphing calculator for some other course, and that's fine. It'll do what you need it to. Maybe I shouldn't admit this, but I have never actually owned one of those myself. I just never got to the point where I felt like I needed it. For my course, anyhow, all you need, if it was a more sophisticated course, yeah, I'd have one, but your basic scientific calculator that has trig functions and scientific notation, and that's all you really need as far as I'm concerned. I have actually seen them in the Dollar Tree. I don't know if a Dollar Tree calculator lasts a whole semester. I've never bought one there to try it out, but typical TI, what is it, TI 30, TI 35? Why can't I remember? They're a more typical price is 10 or 15 bucks, and you can buy them anywhere. Well, you can't buy them at the grocery store, I suppose, but the other things on the list all are there because of doing the course remotely. They weren't there last year. Hopefully they won't be there next year. But for this time around, anyhow, the lectures are all going to be what we're doing right now. Okay. You're only going to meet me face to face for labs and as much of the testing as I can fit in once a week. So the college administration and also SUNY is trying to minimize person-to-person contact because, of course, of the pandemic. So you need access to a computer with a webcam. The webcam is for when we do tests. Okay. Uh, I mean, you can do Zoom with just your voice, but or actually you don't have to say anything at all. You can just watch the videos on. But the webcam is how I'm going to proctor the tests. I'm going to watch you through the camera and make sure you're not being naughty. Access to high-speed internet, obviously, and some way to send me your papers remotely. Um, if there's a quiz, this isn't just a multiple choice kind of thing where I can just have it on the computer screen and you click the right answer. I want to look at your work and see how you did it, because there's a lot of difference between somebody who just lost a minus sign between one line of a calculation and the next. That person basically knows what they're doing and just lost, that's like half a point off on a 10-point quiz. There's a lot of difference between that and somebody who is just totally, completely clueless and deserves, well, I always give people 1 point out of 10 just for showing up, but basically deserves nothing. So if I'm going to be able to read through your work and see how you did it, you have to actually send me an image of your quiz. And if you're doing labs remotely, you'll need to be able to which will happen at least once for everybody, because they're not letting anybody back on campus after Thanksgiving. The idea being at Thanksgiving, people travel, they go mix with a lot of other people at gatherings, and then since there's only 2 weeks left in the semester anyhow, they don't want them coming back and spreading their germs. And so anyhow, either a scanner or just take a picture of it with your phone. Somehow you have to be able to transmit your papers to me when you finish them. Probably not a bad idea to keep the original for a little while in case something goes wrong with transmitting it. So that's all of the stuff that you have to have. Anticipated schedule. As you can see, we're going to meet once a week on Fridays. Start out with a quiz or sometimes an exam. When you finish that, we do the lab for that week. There are a few times, well, like the very first quiz is Wednesday the 9th, because doing it the same day as the lab on September 4th just seemed a little bit too soon to me. It's like you only started the course 5 days ago. Let's give them the weekend to get ready for the quiz. And of course, Monday's a holiday. It's Labor Day. So anyhow, we'll do that one remotely using Zoom and, like I was just talking about, transmit the paper to me. And thereafter, the next time we have a remote quiz will be the week when the first exam comes along, because having a quiz and an exam the same day seemed like a bit much. So anyhow, you can read through that and see what's going on. But typically, a quiz and a lab on Fridays, and watch these recordings of the lectures whenever you want to. Before the quiz is probably a better idea than after the quiz. So let's see, scrolling on down. Grading system. There's a quiz typically once a week. The quizzes are quizzes on the homework, okay? I do not collect the homework because the few times I've tried that, it's always, it just doesn't seem to work very well. I mean, I know everybody else does it, But you know, I get 4 papers and they've all got the same arithmetic mistake. And that's one person who actually did the homework and 3 that were just sitting there going, oh, and what did you have next? And you don't learn anything that way. So the way I like to put it is instead of collecting the homework as in hand it to me, I like to collect it out of your head. Um, the quiz that's waiting for you, actually, I haven't put it together yet, but the quiz that will be waiting for you on that Wednesday, I think I said it was the 9th, whatever it says on the schedule there. If you scroll ahead in the syllabus here to, I think it's page 8, if I remember right. After a few introductory sentences, it says quiz A, and there's a few questions. And then it says quiz B, and there's a few questions. And quiz C and quiz D, all the way through quiz F. I select one of those 6 quizzes at random. And people sometimes go, oh, he wouldn't ask this, you know. I think he's going to ask that. He talked about it a lot. No, when I say at random, I mean it. I used to throw dice to select which quiz, you know, if it comes up 1, I give you quiz A. Comes up 2, I give you quiz B. I've gotten so I use the random number generator in Excel instead of actually throwing dice. But one of the quizzes will be selected at random. I will change the numbers so that you can't just look at it and say, oh, I remember that one. The answer was 4.17. No, change the numbers. Now the answer is 12.8. Okay. But aside from changing the numbers so that you actually have to work through it and know what you're doing, it'll be word for word out of the homework. The way I make a quiz is I bring up the syllabus on my computer. I block and copy one of the quizzes right out of the assignment, paste it into a separate document, spread things out so there's some room to write in between the questions. Have it printed up, and that's the quiz. So the way to prepare is to sit down. You need to get so that you can sit down with the questions and the formula sheet and your calculator and some blank paper. And if you can get it to come out right at home, kind of like a dress rehearsal for the quiz, if you can do that at home and get the right answer, you should be able to walk into class and do exactly the same thing and get the right answer. Okay? Somehow that never seems to work out that way. It's not that often I get somebody with a string of 10s across the homework, but well, I'm not sure I could get a string of 10s on all 14 quizzes because sooner or later I would drop a minus sign and get a 9.5. But anyhow, that's what the quizzes are. 10 points each, typically 1 a week, and they are quizzes on the homework. That's your incentive to keep up with the work, is that you'll be quizzed on it. Once a week, there's a lab. Roughly once a month, we'll have a 100-point exam. Unlike the quizzes, they are not just recycled homework questions. I mean, there'll be questions on the same stuff. There'll be questions that could have been in the homework, but unlike the homework, you have to figure them out on the spot. So you need to actually understand the material, okay? As I think I mentioned a few minutes ago, I have solutions to all the homework posted on the website. So somebody who's good at memorizing stuff could just go there and memorize how to do each quiz and get a real good grade on the quiz each week. And the quizzes are something like 19% of your total points available in the course. The bulk of the points come from the exams, where you have to actually understand the material and figure it out. And so, well, here's the right way. I just got done with the wrong way to study. Okay, this is not a course about memorization. I mean, there's some memorization in every course, but primarily this is a course about developing skills. So the way you develop skills is by practicing. If you're going to learn how to swim, you know, maybe sitting by the side of the pool and watching somebody else swim for a little while is helpful. And in the same way, sitting there and watching me solve physics problems for a little while is helpful. But after a certain point, it doesn't really add anything. You can sit there and watch somebody swim around in a pool for a week solid, and when I throw you in the deep end, you're still going to drown. Okay. You have to get in the water. Probably start on the shallow end is a good idea. Splash around, get a feel for it, and, practice. And in the same way, you need to get your fingers into solving physics problems. And so the right way to do it is to sit down with the homework assignment, try and fight your way through it. At a certain point, if you're not getting the right, I mean, the answer is written right after the problem. At a certain point, if you're not getting the right answer, then you're just pointlessly spinning your wheels. You should refer to the solutions I've got on the website to get yourself unstuck. But after you've peeked at those, put it away, see if you can do it yourself now. Okay. And also, as far as studying for the exams, after a certain point, doing the same problems over and over again, you get into what the economists call diminishing returns on that. If you feel you need more practice, it's better to do 5 new problems rather than do the same old problem 5 times over again. So maybe some of the other end of chapter problems out of the textbook, or some of them you can find solutions in there used to be a student solutions manual, and they don't do that anymore. You have to use their website. Anyhow, that's the story on the exams, and there's also a comprehensive final exam. In other words, it's on the whole course at the end. Where your grade for the course comes from is I just add everything up. A point's a point no matter where it comes from. A point on the final exam isn't worth any more or less than a point on one of the labs. I just add them up. No fancy weighted averaging. And obviously, the more points you get, the happier you are at the end of the semester. Maybe I should just comment on a couple of these other things here. Retests. Unlike some other courses that you might take from somebody else, I do not drop any grades. My philosophy is that instead of me getting rid of bad grades for you, you need to get rid of bad grades for yourself if you want to get rid of them. So I will have another quiz out of the same assignment. Okay, another one of those 6 quizzes with the numbers changed. What I usually do is I just grab a quiz from 3 years ago or whatever, and got a few copies of that one left. The better if you can take it over, the better of the 2 grades counts. The only thing you have to lose by trying is that I only allow a limited number of retakes. There's 14 quizzes in the entire course, and you get to retake a maximum of 5 of them. That seems to be enough for anybody who isn't just using the retakes to procrastinate. As of right now, there are 20 people signed up for the course. Might be a few more by the time we actually start. In a class that size, typically 2 or 3 of them max out by the time we get to the end of the course. So anyhow, you can retake up to 5 of the quizzes. Also, the 3 exams, you get to take 1 of them over again after the 3rd exam so that everybody knows what their worst grade was. And the easiest way to do it would be during the lab period, maybe the deadline is 1 week, okay? So 1 week later during the lab period would be a good time to do it, although if you want to work something out to do it remotely, we can do that also. Incidentally, as it says there in the syllabus, as you've been reading through it, I prefer that students come in and actually do the quizzes and labs in person, but I know there are some of you who that is not what you prefer, probably for some very good reasons. It's like, yeah, my 90-year-old grandmother lives with us, and if I bring home any germs, we're going to kill her. And there is a remote option. I'm not going to take the time. I've already rambled for too long here about the syllabus, but read through the syllabus and explains and send me any questions, send me an email or whatever. You can do the labs remotely, you can do the quizzes remotely. You have the option of never setting foot in my classroom all semester long. What we're doing right now will be the closest you ever get to me and the other students, if you'd rather do it that way. You have that option. But if you're comfortable with it, a real lab experience involves actually doing the experiment yourself, and actually, because, you know, a video of me running through the lab, I've done these labs a million times. It's going to go pretty smoothly. And if it doesn't, I'm going to pause the recording and do it over. A part of the experience is just simply fighting with the equipment and fighting with the software and getting it to work. And that's because that's, you know, that's the real world. I'm just going to say a couple of words about the thing that says, is this the right physics course for you? Because imagine this, sometimes people get badly advised. So the 131 sequence, 131, 132, there's also a physics 133. 132 and 133 are both spring courses. I'll talk to you more about that around midterm when it's time to register for the spring, or if you want more information sooner, just ask. But anyhow, they are, this sequence, the 131 sequence, is where I go in and do it right. No cutting of corners and no, well, I mean, you always skip over something because you don't have an infinite amount of time, but you can take this course and be a physics major. We don't get that many physics majors. Last year I didn't have any at all. Probably the biggest single group, they're not a majority of the class usually, but the biggest single group is usually engineering majors, as in people who are going to go get a BS degree and become licensed engineers. And, you know, a variety of other science-related majors. I think somebody told me once that if you go to Brockport and major in meteorology, at least at the time that I was talking to that person, they wanted this as a calculus-based course. So the best advice is to be your own advisor to some extent. Go to the websites of the four-year schools that you're considering, look at what they require, and get it all figured out. And don't let some well-intentioned person at GCC, like me, mislead you, okay? But you can apply this course to any major. I mean, if you're an engineering major, this course will work. If you're a drama major, this course will work. But, you know, drama majors who are taking calculus are kind of few and far between. Drama majors would typically take physics 100. There's a lot less math. It's a 3-credit course instead of a 4-credit course. Anybody who's in an unrelated major, you know, business or criminal justice or whatever, physics 100. The 121, 122 sequence, the algebra trig-based course, that's for people who in majors that are somewhat related to physics. Drafting majors go through that course. Again, you can take this course. You're never going to get in any trouble where somebody looks at your transcript and says, oh, you learned too much. You have to take this other course where some of that stuff has been left out. You know, when in doubt, if you can manage it, take the better course. But that is all that's necessary. The 121 sequence is all that's necessary for a drafting major, or for transfer programs, like if you want to be a physical therapists, take physics. See the connection there? And, you know, a variety of other health-related fields and other things like that. Pharmacists can take the algebra trig-based sequence, and so on. So any questions about that, send them to me. But like I said, the best thing to do is do your homework and be your own advisor. Okay, that's enough time spent discoursing on the syllabus. Let me pause this for a moment and get the camera aimed the other way. Okay, one of those handouts that I give out the first day that I mentioned earlier is this one here that says outline of lecture notes, which is exactly what it is. It's an outline of what I'm going to be talking about in class. Like it says here in the parentheses, it's not everything. I mean, I'm going to be writing on here starting in a moment because I think taking notes is important, okay? If you just sit there in a classroom where some guy is flipping through PowerPoint slides and droning on while you sit in the dark, in about 10 minutes, you're going to be asleep or looking out the window or something like that. I think taking notes keeps you focused on what's going on. So even though you're at home rather than in a class, my advice is that you pretend you're in a classroom and get a notebook to take notes in. I mean, yeah, you can play the video back over and over again if you want, but even if you never look at them once, I think, in my opinion anyhow, I think the act of creating the notes is helpful. Forces you to focus on what's going on. So that's my advice on that. First unit of the course is straight line motion, okay? One-dimensional motion, in other words. In a couple of weeks, I forget whether it's section 3 or section 4, we'll branch out and deal with motion in 2 dimensions. We aren't going to do too much in 3 dimensions. It'll come up occasionally, but the description of 3-dimensional motion is actually just an extension of how you do it in 2 dimensions. So it's not that big of a further leap. But for the first week, we restrict ourselves to motion along a straight line because it's the simplest case, and then you build from there. So we start out with some definitions. Incidentally, it's probably less critical to print out this handout than it is the formula sheet because this will be on camera quite a bit anyhow. And maybe you want to just recopy things into your notes as you're taking them, or that's for you to figure out, I guess. But the only advantage of having a hard copy sitting next to you probably would be that it a little bit better focus than what we get here. But definitions. In any course, whether it's physics or psychology or anything else, quite often the right answer to the question depends on exactly what the words mean. So the place to start out is with exactly what do the words mean. And the first word is going to be displacement. So displacement yes, I'm writing in cursive. I'm old people write in cursive, deal with it. But, you know, I will read out loud everything I'm writing down. So if you can't decipher my handwriting, you'll hear me say it anyhow. When I went to elementary school, we didn't even call it cursive. We just called it writing. First grade, we learned how to print. Third grade, we started learning how to write. It was just writing. Anyhow, displacement, distance and direction that something moved. So I said for the time being that we're considering something moving along a straight line. So here is the straight line. This could be some highway like the thruway, except the real thruway has curves and hills and things like that in it that complicate things a little bit. But if you imagine a perfectly straight, perfectly flat throughway, there's those mileposts on the side of the road. You've got milepost. I don't think they actually have a zero, but they're counting from, I believe it's the city line in Yonkers is where the throughway officially begins. And you go a mile down the road and there's a sign with a 1 on it. And you go another mile down the road and there's a sign with a 2 on it. And actually they've got little signs with tenths of a mile in between. And it goes on like that. We're going to call this the x-axis. So it's a number line, okay? If you're going on vacation, you call it the throughway. If you're in a math class, you call it a number line. One difference, I suppose, between a number line and the throughway is that if you're going the other way, there are negative numbers on a number line. And let's say that your car, at some particular moment that you're interested in, is here. Sometimes I print instead of write for no particularly good reason. And a little while later, so when you first look out the window, you notice that the car is right next to milepost 1. And a little while later, you look out the window again, and you notice that the car is right next to milepost 3. The displacement is delta x, meaning x final minus x initial. F for final, I for initial. X means where are you on the x-axis. Delta anything means final minus initial. I mean, it's a piece of notation that's going to come up over and over and over again. Change in the pressure of a gas, final minus initial. Change in temperature, final minus initial. Change in voltage, final minus initial. Always final minus initial, never initial minus final. Okay, so you started out here, you ended up there. How far did you move? X equals 3, subtract off x equals 1, 3 minus 1, you moved 2. If it's the throughway, it would be measured in miles, 2 miles, okay? So that's what displacement means. Average velocity. Displacement divided by time. If you went 100 miles in 2 hours, 100 miles divided by 2 hours, 50 miles per hour for your average velocity. Anytime you hear the word per, it means divide, okay? Miles per gallon means you take the miles and divide by the gallons. Miles per hour means miles divided by hours. So displacement divided by time. Now, you probably weren't driving down the throughway at 50 miles per hour for 2 hours. Rather, most people do something in the low to the mid 70s, 72, 75 miles per hour, something like that on the throughway. But there was somewhere in there where you stopped at one of the service areas for a while. And so even though there was almost no moment when you were driving 50 miles an hour, you were almost always going either faster than that or stopped. What it averages out to for the whole 2 hours is 50 miles per hour. Okay, that's what it means by average velocity. not the velocity you had for the whole 2 hours, but when you put it all together, that's what it averages out to, including being stopped for a little while and having a velocity of 0. Physicists try to be as lazy as possible about what they write down, make their notation nice and compact so it takes less time and less space. And so instead of writing out a phrase like average velocity, usually we do something more like V for velocity and put some sort of a subscript on it that means average. Instead of writing out the word displacement, we can just call it delta x. And the corresponding change in time would be delta t. And so that says the same thing as that, just in a handier, more compact, easier to write notation. Average velocity, displacement divided by time. So what have we got next here? Slope of a graph. A concept you should already be familiar with from some previous math course. You've got a line on a graph, and a slope is a number that describes the steepness of that line. If the slope is a big number, that means a steep line. If the slope is a small number, that's a not so steep line. If the slope is 0, that's a horizontal line. If the slope is negative, that means the line runs downhill instead of uphill, okay? On the usual XY coordinate system, the slope would be delta y over delta x. Now, what if you don't have the axes labeled with the usual x and y? What if you set up a graph like this? Why would you do that? Well, because you want to graph where the car is located as a function of time. And the real convention for how you draw graphs isn't in terms of what letters of the alphabet you use. I mean, if seeing X on the vertical axis really upsets you that much, maybe you can use P for position or something like that. But whatever letters you're using, the independent variable belongs on the horizontal axis, the dependent variable up here. This is a function of that, not the other way around. If the car shifts in reverse and drives back to milepost number 1, it does not make every clock in the universe run backwards. The position is a function of the time. It's not a matter of the time being a function of the position. So I guess one thing I could say along with that is that anytime you've got a graph with time on it, whether it's position versus time, or pressure as a function of time, or voltage versus time, or whatever, time always goes on the horizontal axis because other things are always functions of time. Time flows on no matter what. So if you've got a graph, on this graph, a line on this graph, and you pick a couple of points and you do the slope like was on the note packet that I had here a moment ago. The horizontal run, instead of being delta x, well, we've got t down here where x used to be, so the horizontal run is delta t. And the vertical rise, well, I've got x where y would normally be, so this would be delta x for the rise. And the slope, as always, slope is rise over run. So if the graph is set up like this, instead of delta y over delta x, you've got delta x over delta t, which I just got done saying is the velocity of whatever it is you're talking about, a car on a road or whatever. So the moral of this story is that if you have a graph of position versus time, the object's velocity is the slope. So just a few examples to go along with that. Position as a function of time. This is pretty much the same graph I had there again, but if the graph looks like that, well, that's, a line that runs uphill has a positive slope, which means that the car has a positive velocity, which means it's moving toward the right. Okay, if for contrast, if you've got a line like that, the velocity is negative. Downhill line has a negative slope. If the car is moving toward the left, the velocity comes out negative, because when you do final minus initial, if you turn the arrow around so that this is before and this is after, then instead of doing 3 minus 1, you're doing 1 minus 3. Okay? And so if the thing is going toward the left, delta x will be negative, and that makes the velocity negative. In general, with delta anything, change in position, change in temperature, whatever, increases are positive, decreases are negative. Okay, so if the car is headed toward an increasing value of x, it'll have a positive velocity, and if it's heading toward a decreasing value of x, it'll have a negative velocity. And so the plus or minus sign gives you the direction. All of these things I'm talking about right now, displacement, velocity, I'll get to acceleration soon, they're all what are called vectors, which I'll explain properly in section 2, but the short version of the story is just to say that they are things that have a direction. And the way you handle the direction in the case of one-dimensional motion is just with a plus or minus sign. If the displacement points that way, it's positive. If the displacement points that way, it's negative. If the velocity is that way, it's positive. That way is negative. Same with acceleration. That way is positive. That way is negative. And the plus and minus signs, by the way, are all independent of each other. Just because x is positive doesn't mean that v also has to be positive. Like here, x is positive, v is negative. And you could do something the other way around. On this graph over here, what if the line had been down there instead, where x is negative? Well, x is negative, but it's increasing, negative 4, negative 3, negative 2, negative 1, increasing in the sense of becoming less negative. And so x is negative, v is positive. The two things are independent of each other. One more graph. Again, position as a function of time. And what if you had one that looks kind of like that? I usually turn around and say to the class, what's going on here? And today when I do that, none of you seem to be saying anything. So I'll just go ahead and tell you this would be an increasing velocity. In other words, the car is accelerating. The velocity is the slope, and the slope means the steepness. As time goes by, the graph is getting steeper and steeper and steeper, which means a greater and greater slope, which means a greater and greater velocity. It's picking up speed. So notice that velocity is the slope of a displacement graph. Example, I chose a school bus because a school bus, as you've noticed if you've ever been stuck behind one, a school bus changes its velocity a lot. The kid gets on, the bus picks up speed. Before you know it, the bus slows down and stops for the next kid. The kid gets on, it picks up speed, and it's constantly changing. Let's say that in 15 minutes, the bus goes 5 miles. That makes its average velocity 20 miles per hour. But like I said about the car that stops at the rest area on the thruway, there are very few times during that 15 minutes when the bus is actually going 20 miles an hour. Usually it's either going faster or slower, just passes through 20 miles an hour every now and then. But that's what it averages out to for the whole 15 minutes. Notice, by the way, you can't just say, well, you could just say 5 divided by 15. But if you do that, the velocity will come out in miles per minute. In any kind of a calculation, whatever units you put in will be the units you get out. Miles divided by minutes will give you miles per minute. If you want miles per hour, which would be the more conventional way of describing your speed, you need to convert the minutes into hours. Notice a complete answer includes the appropriate units. If this, well, you're not going to be so lucky as to have a problem as trivial as this one on a quiz, but if you did, and for the answer you just wrote down a 20 and put a little box around it and smiled to yourself as you handed in the paper because you figured you had it right, well, actually your quiz is going to come back with 9.5 out of 10 on it because you didn't label the unit. Why do I make a big issue out of this? Well, my favorite story for that involves something called the Mars Climate Orbiter, which was a spacecraft launched in the late 1990s. If you're interested, I'm sure if you Google it, you can get more details. But the thing is, you know, they launched the spacecraft. They spent $125 million building it. That's in mid-1990s dollars. It would probably be twice that much today. So they launch it. It takes a long time. It finally gets to Mars many, many months later, and it's time to put it into orbit, which means you have to slow it down by running the engine for a little while. Well, you see, the design team I guess they were based in Colorado, at least at that time, I don't know if anybody does this anymore, but at least at that time, they were still working in feet and pounds and that system of units. But the navigation team in California, the guys that were actually flying this thing, they were working in metric units, newtons and meters instead of pounds and feet. And so the thrust that they thought was in newtons was actually in pounds. Well, a pound is more than 4 newtons. So they were getting a lot more thrust than they were basing their calculations on. So when they ran the engine, the spacecraft didn't just drop into orbit, it just dropped, as in $125 million scattered all around, all over the surface of Mars. So yes, it is important to pay attention to the units on your numbers. If a weight falls on your foot, it makes a lot of difference if it's 4 ounces or 4 tons. A number by itself is meaningless unless you put the units on it. And the reason that I keep insisting on that over and over and over again is that if someday you crash a spacecraft onto Mars, that is a good way of spending the rest of your working life making sandwiches in a delicatessen somewhere. So label the units. Example number 1, section 1, example 1. The same school bus, only we're going to watch it for a little bit longer. 15 minutes out, 15 minutes back. So in half an hour, It goes 10 miles and returns to the school. Find the average velocity. And everybody is sitting out there saying to themselves, well, that would just be 20 miles an hour again, right? And no, blah, you have fallen into my little trap. The answer is not 20 miles an hour. The correct answer is 0. And here's how that works. Velocity, average. That's what the question said to find. Find the average velocity. So like it says in the box a little further up your notes here, delta x over delta t. The question tells us that the bus covered a total distance of 10 miles. This is irrelevant information. Delta x does not mean how many miles did you run up on the bus's odometer. Delta x means how far from where you started to where you ended up. And in the case of the school bus, where it started and where it ended up are the same place, okay, at the school. So delta x is 0 because delta x means x final minus x initial, and both x final and x initial are the same place on the x-axis. Both of them are the location of the school. So delta x is x final minus x initial, and x final equals x initial. Times half an hour, and when you divide, it's an average velocity of 0. You see, velocity, as I said earlier, is a vector. You include its direction by whether it's positive or negative. So when the bus was heading out from the school, it had a positive velocity. During the second half of the trip, it had a negative velocity. And when you take all of those positive and negative numbers and add them up to do the average, the pluses and minuses cancel each other out. And that's how the average comes out 0, okay? The average speed of the bus is 20 miles per hour. Now, people use the words velocity and speed pretty much interchangeably in everyday common, standing on a street corner type usage. But if you get into precise definitions, they don't mean quite the same thing. Velocity is displacement divided by time. Speed is the distance covered divided by the time. In other words, in the one case, the direction matters. In the other case, it doesn't. Velocity is a vector, speed is a scalar. So, again, words that I'll define in section 2. So, another example, meant to lead into the idea of instantaneous velocity, okay? Over the whole half hour, the bus has an average velocity of 0, or during the first 15 minutes, it had an average velocity of 20. Well, what if you don't want to know the average over an extended period of time? What if you want to know what is the velocity of the bus at some exact instant, okay? How fast was it going and at what direction at 7:51 and 12 seconds a.m., okay? Right exactly then, how fast was it going? Instantaneous velocity. Well, this graph here probably doesn't represent the motion of a school bus because it's only 10 seconds long, but it's the same general idea. you've got something that's moving toward the right, and then it stops for a couple of seconds, and then it moves further toward the right, and then for the last 2.5 seconds, it moves back toward the left again. Downhill line is a negative slope, so its velocity would be in the negative direction. And by the time you get to 10 seconds, it's back to x equals 0 where it started. What is the velocity of the object that this graph refers to? What is its velocity at this instant? T equals 7 seconds, right about there. Okay. Well, you know, doing the delta x equals 0, delta t equals 10 isn't going to tell you the velocity then. It's going to tell you that you've got 0 for the whole 10 seconds, but the thing wasn't moving at a velocity of 0 at that particular instant. So what do you do to get the instantaneous velocity? The answer is you have to use a smaller time interval. Like it says in the parentheses, use a delta t small enough that the slope doesn't change. Like from t equals 6 to t equals 7.5, you've got a nice straight line there. Straight line has the same slope everywhere. So that would, and that includes the instant that we're interested in. So that would be a small enough time interval to tell us what was the velocity at that instant. And it's about time to go to a fresh sheet of paper. And I guess this is called 1-2. Section 1, example 2. Just to repeat what I already had printed on the handout because it's an important point, the way you get the instantaneous velocity is you have to use a time interval small enough that the velocity doesn't change. Okay? If you want the instantaneous velocity of a school bus, maybe use a delta t that's just a few seconds long because, you know, school buses don't accelerate very quickly and you'll have pretty much a constant velocity during such a short time interval. So in this case, velocity is delta x over delta t. I didn't put an AV subscript on it because this time I'm calculating the instantaneous velocity. Okay, small enough time interval that instantaneous and average are the same thing. X final minus X initial. Well, maybe I should start on the bottom. T final minus T initial. Final time, 7.5 seconds. Initial time, 6 seconds. At T equals 7.5, the whatever it was, the object we're talking about, was located at X equals 30. At T equals 6, it was located at X equals 20. So where I'm getting those numbers from is right here, X final and T final. Okay, at T equals 7.5, it's at X equals 30. And for initial values, at T equals 6, it's located at X equals 20. So you fill those in. 30 minus 20 is 10 meters. That minus that is 1.5 seconds. And 10 divided by 1.5 gives you 6.67. As for the units, meters divided by seconds gives you, you'll never guess, meters per second. Okay, well, that example is kind of a nice stepping stone. It's a good exercise for instructional purposes, but not completely realistic. In the real world, the graph wouldn't have these sharp corners, these cusps, okay? Because what you've got here, for the first 4 seconds, 20 meters in 4 seconds, that would be 5 meters per second, okay? So this thing was going along at 5 meters per second, and then from this point onward, it has a velocity of 0 for the next couple of seconds. Well, the problem is it didn't pass through any of the numbers in between. It went right straight from being 5 meters per second to being 0 meters per second without ever being 4, 3, 2, or 1. Just and all of a sudden it stopped. And that's unphysical. I mean, that just does not happen in the real world. So what's more realistic is if something is going along at a certain speed, as it loses speed, the graph will curve until it's finally stopped. And then when it starts to move again, it'll start curving the other way as it picks up speed. And then, you know, as it stops moving one way and starts going the other way, again, the slope will pass through all of the in-between values as it curves around up here. And so in the real world, you don't have joined line segments. You're always going to have some sort of a curve that, or some sort of a graph that curves, which then leads into the question, if you've got a curved graph, how do you define the slope at a point? Okay, delta x over delta t, or delta y over delta x, if you'd rather think of it that way. That definition is for the slope of a line. What do you do when it's not a line? How do you get a number that tells you how steep the graph is at this particular point? If you go to the next point over, it's not quite as steep on the left, and if you go to the next point over on the right, it's a little bit steeper there. How do you get the slope at this point? Well, it's kind of an extension of this idea here. Use a time interval small enough that the velocity doesn't change. Well, it always changes when the thing's curving, but maybe you could put a couple of words on the end that it doesn't change enough to matter. It's what I like to call a flat Earth approximation. It's not a term I've ever seen in a textbook, but I like it. The idea that I have is that as most people are aware, some people believe the most amazing things, but as most people are aware, the Earth is round. But, you know, if you're just sitting on a park bench and decide to toss a ball to your friend who's on the next bench over 20 feet away, you don't really take the curvature of the Earth into account as you toss the ball. Over short distances like that, you can think of the Earth as flat. And in much the same way, if you look at a really, really small part of this curve, a sufficiently small part of the curve looks like a straight line, at least to a certain level of accuracy. So I said something before about determining the speed of the school bus based on just a few seconds. But of course, actually, even in a few seconds, the bus could gain a little bit of speed or slow down some. So what would be even better would be to get some elaborate electronic equipment and measure things on a time interval of just like 1/100th of a second. To any reasonable level of accuracy, it is going to be constant during 1/100th of a second. But of course, what if you want to go to an unreasonable level of accuracy? Once you get several places past the decimal point, the speed of the bus is still changing. And so you would need an even smaller time interval to make it an even better approximation. Well, what's going to make the approximation exact is if you imagine the time interval collapsing completely. onto the interval that you're interested in. So the approximation becomes exact as delta t approaches 0, which leads to the definition of instantaneous velocity. As I fumble with my glasses and my pen, instantaneous velocity. V for velocity. Those of you in Calc 1 are probably just starting to do limits at this point. This is red. I mean, as usual, it's sort of an abbreviated shorthand kind of thing. But if you read it out without abbreviating anything, it's read the limit as delta t approaches 0. So the limit as delta t approaches 0 of delta x over delta t. And so that would be the definition of instantaneous velocity. And what it means is that process that I was just taught. What it really is it's a sneaky, underhanded way of dividing by 0. Okay, ever since you first learned how to divide in like 3rd or 4th or 2nd grade or somewhere around in there, somebody's probably been pounding into you, you can't divide by 0. You can't divide by 0. Bad, 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 bad. Well, somebody found a loophole. So you want to divide by delta t. Delta t is not 0. You imagine delta t collapsing onto the point on the graph that you're interested in. So as it shrinks, delta t approaches, but it's not 0. It's really, really small and getting smaller all the time. And as delta t approaches 0, what value does this ratio approach? And that's how you get away with dividing by 0 without dividing by 0. That's what's going on here, really. But there's a shorthand notation for this. Instead of writing all that out about a limit and all of that, you've got that, or simply dx over dt for the definition of instantaneous velocity. This particular type of limit, this particular example of a limit, is called a derivative. Actually, if you get into the history of the subject, it's exactly the opposite of the way it's presented now in calculus class. When you take Calc 1, you start out with limits and you spend a few weeks on that. And then once you've done that, you get to this kind of thing and start covering derivatives. And actually, historically, it was the other way around. Isaac Newton originally discovered or developed the idea of a derivative in the late 1600s. And independently in Germany, Gottfried Leibniz independently discovered the same principle. And a lot of people resisted it, going, you can't do that. That doesn't make any sense. And many years later, the idea of a limit was developed as a way of explaining, yeah, you can do that. This would be why. And everyone kind of went, oh, yeah, okay, I guess so. But anyhow, maybe take a minute and clarify the notation. As I've already said, V average means the average velocity. When you see just plain V without the subscript, that means the instantaneous, like right here, that's the instantaneous velocity, the velocity at an instant instead of averaged during some time delta t. It's a really bad N. So instantaneous velocity using a D, like I did over here, instead of a delta, like I did up here, means the interval is infinitesimal. Infinitesimal meaning vanishingly small. You're going through this thought process where you imagine the intervals, delta x and delta t, collapsing onto the instant you want to know about. And as they approach zero, what value does this ratio approach? So that's the notation. Back to the note packet. We have completed our first page, the first of many. Mathematical background. So we are in the uncomfortable position here of having gotten several weeks out ahead of your math course. Some of you are probably in, further along, like, maybe you're in Calc 3. And if you are, that's great, because you can sit there and kind of move your lips along with me that way. But many of the students in this class are just starting Calc 1. That is the level that the student is assumed to be at. And if you know more, so much the better. But you're not going to, if you're in Calc 1, you're not going to get to derivatives for several weeks. So what I need to do is take a few minutes to give you a working knowledge of derivatives, and then the details will be filled out for you, and that's why you take the math class. But to summarize it all down into about 5 minutes worth of stuff, a derivative gives the slope of the graph at the point that you're interested in. Now, how do you find the derivative of a given function? Well, that depends on what kind of a function it is. For the moment, we're going to stick to polynomial functions, something like 3x to the 7th power or something like that, okay? Several terms like that added together, polynomial. If that's your function, a would be the 3, n would be the 7, 3x to the 7th power, then the derivative of that function would be, well, the constant coefficient. You just copy it over. It just sits there and watches the rest of it, without doing anything itself. As for the thing that it's multiplied by, you bring the old exponent down and write it in front, and for your new exponent, you reduce it by 1. Okay, so the derivative of x to the 7th power would be 7x to the 6th power, assuming a and n are non-zero constants. If n is equal to 0, in other words, you just got y equals a, because x to the 0 would just be equal to 1. The derivative of a constant is 0. which goes back to the idea that this is the slope of a graph. If you've got y, some constant function like y equals 7, when you graph that, it's a horizontal line. And a horizontal line has a slope of 0. Now, the formula sheet. I said your best friend as far as this course goes. The first several pages are various formulas labeled by which part of the course they refer to. And then once you get past the last unit in the course, section 14, there's other useful stuff back here. I mean, there's tables of thermal conductivities and specific heats and things, but thrown in with that also is actually altogether almost a whole page of mathematical background where you can, remember, you get to refer to this when there's a test. You don't get to use your textbook. You don't get to use your lecture notes. You certainly don't get to connect to the internet and look at my homework solutions. But this is what I figured was good to provide to you to de-emphasize memorization in this course. So there's all kinds of good stuff here. Various geometric formulas like the area of a circle. Here's the quadratic formula. You might need that every now and then. A little background information about logarithms. Turn the page, and here is the part that I was thinking of for right now. Here's everything I just said in class about how to do the derivative of a polynomial function. It's a little out of focus, but it's right there. In fact, I even did an example for you. So how's that for helpful? What a guy. Now, as I said, this is kind of a narrow case that we're restricting ourselves to. There are lots of functions that are not polynomials, like if y equals the sine of x, you're not going to find its derivative this way. Derivative of sine happens to be cosine. And that's sines and logarithms and things like that are all stories for another day. But just to kind of get things rolling, here's how you do a polynomial function. So as an example of that, let's say an object's position as a function of time is given by this function here. How you would realistically know that, well, that's a story for another day also. But as far as, for purposes of this problem, just by some sort of divine inspiration, you know that this is the position as a function of time. The question is to find its velocity at this particular instant. So here we go on that one. Kind of a two-step process. First of all, you have to find the derivative of that function that you were given. So maybe I should copy it over as a starting point. If x equals 7t to the third plus 4t plus 8, where x is measured in meters and t is measured in seconds. Always keep an eye on the units. Well, using the rules I was just talking about, you recopy the 7. The constant coefficient just kind of sits around and does nothing. The derivative of t to the third power would be 3 times t to the 3 minus 1. Again, next term. The derivative of a sum is the sum of the derivatives, so you just differentiate term by term. The 4 just gets recopied. T means t to the first power. So again, reducing the exponent by 1 would be t to the 1 minus 1, t to the 0 power. And on the end, 8 is a constant. The derivative of a constant is 0. Simplifying that a little bit, 7 times 3 is 21. 3 minus 1 is 2. T to the 0 power is 1. 1 times 4 is 4. Okay, so I should have labeled, this isn't equal to x anymore. This is the derivative of x with respect to time. So that's the velocity at any time t. To find the velocity at t equals 2, stick 2 in where the letter t is. So step 2 is to evaluate the derivative. Evaluate at t equals 2 seconds. So 21, put in 2 where the letter t used to be. And at that particular moment, it's going 88 meters per second. And I think I'm going to end this particular recording here. Normally, of course, the class gets divided up into 3 55-minute segments each week. But, of course, part of that gets used up for the quiz, which won't be part of the recordings here. But, you know, a 2.5-hour recording, maybe it's better to divide it into 2 pieces at least. So I think that's what I'm going to do with each unit of the course, is divide it into. Section 7 is particularly long. I might do that one in 3 parts. But anyhow, I am going to stop this here and let this recording percolate, get it posted in Blackboard fairly soon. And in a couple minutes, I'm going to record the second half of section 1, but for your purposes, that'll be a separate recording.